Hello everyone, welcome back to my channel, and today I'm going to talk about classification, multi-class strategies, and the tree-based architectures. So in machine learning, we aren't just coding, we are actually building digital brains. But a brain designed to sort Pokemon into categories shouldn't be the same brain designed to predict the market price of a Black Lotus card. Starting with binary classification, this is the foundation. It's a supervised learning task where the output is a categorical variable with exactly two classes. Let's say we want to predict if a planet in the outer ring is inhabitable or barren. We could select features such as distance from its sun or I don't know, atmospheric composition maybe. So classification isn't about finding a number, but it's about finding a decision boundary or finding labels. One common problem that I actually run into as well when I was building my binary classification model is overfitting. So I was building a model to detect malicious hackers in a network, and my model got 99% of accuracy. And okay, I saw that. I thought like, okay, maybe I'm a genius. I'm the best AI engineer in the world. But actually, I didn't know that at the time, but usually models with too much accuracy are error trap, or they ended up in an error trap. In my case, my model only got 99% of accuracy because like 99% of the traffic was good and just a small bit of the traffic was malicious hackers. So the model just learned to ignore the hackers and just answered that the traffic was good for every input. Therefore, in classification, if your classes are not balanced, accuracy is actually a lie. We gotta look at precision and recall. Precision is basically in telling how many inhabitable planets you count that were actually inhabitable planets, and recall is basically saying how many total inhabitable planets did you miss. The multi-class prediction is basically the sorting hat of Harry Potter because it's used to predict more than two labels. So the problem here is that most binary algorithms like SVMs that we'll see in the next video can naturally see more than two sides. So we have to kind of force them into using two main strategies, one versus all and one versus one. One versus all, basically we separate a model to train for each feature. So for example, in the sorting hat example, we have 4 houses for Harry Potter. So we will have 4 separate models training for each house, and we're gonna compare like Gryffindor versus the rest of the houses, Slytherin versus the rest, and so on. The winner is the one with the highest confidence score. And one versus one is basically creating a tournament, so every house fights every other house. One versus one is computationally more expensive, but it avoids the imbalance problem of one versus all. The decision trees is a model that partitions the data space into rectangles and uses concept called information gain based on entropy. Entropy is our measure of chaos. So imagine that. Let's say we have a leaf of our tree that has both Marvel and DC fans mixed together. In this case, our entropy is high, probably close to 1, which is the highest value possible. If you split them by the question who likes Batman, one side will be now 100% DC fans, so the entropy drops to 0, the lowest value possible. The tree's only goal is to reduce chaos, or entropy value, and to increase information gain. By the way, there's a technique called pruning that it's essential to our model because it stops the tree from memorizing noise and actually start learning patterns. We can apply pruning by min samples leaf in the code, and also we need to set a max depth so that the tree won't grow so huge. A regression tree model is basically the same as the decision tree, but instead of returning a label like hero or DC or Marvel fan, it will return a continuous numerical value. Let's say you want to predict the compute power of a creature in a RPG game based on its level, rarity, and equipment. So you could do that by regression tree. It's a regression model as the same as we saw before. So you calculate the mean squared error, the MSE for each split of the tree, and it's gonna choose the split that results in the lowest variance within the resulting groups. So we've got the concepts, we've got some technical traps that is dangerous and we want to avoid. Now let's build something with all this incredible knowledge we have gathered here in this video, right? So welcome to the Mad Science Lab, the place that will make crazy and mostly unsuccessful experimentations. We'll be predicting students' stats, which is whether they will graduate, drop out, or stay enrolled. And let's go through the code here. I just kind of skip the parts already seen in the previous videos, and we kind of know that already. Alright, so the imports, let's load our data set. You can see here we have 4,424 rows and 37 columns. Okay, our target is the column target. This data is designed to machine learning purposes, so that's why our column name is already target. This notation to make it easy for us. You can pause the video or visualize the data later if you want to on your computer or whatever. So let's first check for the data variable here, for the target variable I mean. Let's see the distribution, and as you can see, it's not really well distributed. We have many more students that graduated than the others. So you gotta handle that, right? Otherwise, our model just gets like graduate for every time because it's the most common and we have a great accuracy. But again, it's gonna be a lie. You're just gonna pass the class weight balanced inside our decision tree later. So it's not gonna be a problem. We just gotta remember that. So let's check for null values. We don't have any null values here. Okay. So it's good. We can check our correlation between the features. So I guess I said that already, but to be honest, I forgot the things I said. But basically we want to avoid the features that are too correlated to each other and too correlated to the target, because often these features that are too correlated to the target are a trap. Like here, for example, if included curricular units second semester approved, our model will just basically ignore all those features and use this as a kind of a God predictor parameter. If you want a honest model here, we gotta take these features below the first three maybe, or we have to keep the balance here, because if you take only these features like that don't have correlation at all, our model won't predict anything at all as well. Yeah, we gotta kind of that see this balance between not too much correlated but not irrelevant as well. So I run some tests already, excluding these features I selected, using only the merit stats, curves, previous qualification, age, and scholarship, but our model didn't go well, so I included this. I made sure not to include these first two because they're too correlated. So this is gonna be our feature, and our target is our target column. We can visualize the features. Now let's separate the categorical features and the numerical features. So why do I encode the categorical features? Because our categorical features here, they are categorical but guided as numbers. So for example here, curse, it's categories, right, of the curses, as well as marital status. So they're numbers, right? So you gotta make sure they are strings to encode, okay? That's why we pass as type strings, and our numerical features will be all columns excluding the categorical features. So we just run this code. Now we separate it and we split. We always split it first before scale or encoding. In this case, we won't need to scale because it's a decision tree, so it doesn't care about scale or not. So let's encode category features. We just pass one hard coder here. And remember, we want to fit only on the training data. We never fit on the test data, okay? Encoding the target is optional in decision trees, but I just do it for best practices. So now we separated the categorical features and numerical features. We gotta concat them together. Before that, we just need to make sure that no rows were lost in this process. So we print the length. If the length is the same, now we can use HS tag, otherwise it will put through a traceback error. We combine the numerical features and the categorical features, right? So let's combine. We can print the final shape. We're gonna init our model with decision tree classifier. Gonna use the entropy as I explained before, and we gotta remember to pass class width balanced because our classes are not balanced here at all. The max depth could change, but after I run some tests, as I said, and I found out that 4 is a great depth. Now we just feed the training and we predict the test as all the others, okay? We can visualize the accuracy. So we got an accuracy of 62%, and we can have our classification report. Of course, this is too big to have a classification report to have like a tree, but basically that's it for decision tree. Not really accurate, but it's real and it's honest. Because imagine that predicting whether a student will graduate or not, or still enrolled, it's kind of difficult based on its information purely. So let's go to regression trees. The same architecture of trees, but instead of classifying, it will predict continuous numerical numbers, right? Let's import, let's load our data and check for null values. It's basically the same process of feature engineering. So in this case, we're gonna predict the global sales of a game. We have some stats here. It's not a really big data. We have only 11 columns and we do have a lot of rows, but the columns will be a problem later. I'll explain why. We can get the null values from the columns, because here it's kind of hard to see. These numbers here are the non-null value count, but you see here year is not equal to those, so we have some in year and publisher, but imagine that if had many columns, it would be hard to see. So we just run this snippet of code. Basically it's the same code as before, but the only difference is that this is better printed and sorted by descending order. So here in here we have some missing count and a publisher missing count, and it's good to show the percentage as well, because 200 here in this case is only one person, but 200 in other case could be like 90% or something. So the way we treat the null values is really gonna depend on the data of the null values. For example, here we have year and publisher. So year we can fill with median, and publisher we can fill with unknown, because some indie games can have no publisher, so it could be unknown. And for year we can kind of get the median of the year the game was released, so it's not gonna be a problem. We just take the year, we fill the null values with the median of the same values, of course, and the publisher will fill the null values with unknown. Let's check the correlation, but we have some categorical features here, some features that are not numbers. For that, we temporarily encode these features, because encoding only goes after splitting again, right? And see the correlation. Here rank, of course, is gonna be the most per correlation, because the first rank here is the most sold and so on. So we definitely not gonna use this, as well as basically these 4 other columns will be useful for us, even though they're not too correlated to our global sales. Why is that? Because rank is basically the global sales ranked, so it's of course gonna be the most correlated. But if we take a close look here, the global sales are basically the sum of all these 4 features, all the sales around the world, right? So if we took these as features, we're not going to be predicting actually. We're just asking our model to sum the sales, and then it's going to return the global sales. We don't really care about the name as well, really. We drop them and we extract our X and Y. Let's separate categorical and numerical features, just like before. So we have the categorical features and numerical features. Everything else is numerical. Again, make sure the categorical features are in string for encoding. So one thing that's important is to check the balance for the features as well. We can do that by checking the non-unique sort values, and we can see that publisher has 578 non-unique values. So what's the problem with that? If we encoded this, we have more than 600 columns. So we don't want that. How do we solve that? We could group these publishers. For example, here I group the publishers with less than 20 entries into other, okay? Imagine that for some games, they'll have a publisher that is not really well known, so they publish a few games, so we can group them into an other column. So we just create this column, and we pass this publisher with less than 20 entries into this column we created, okay? We just gotta get the publisher counts and the publisher with less than 20 entries and replace with others. So now if we pass that, we have only 89, which is still big, but it's not gonna be a problem here. So when I said that feature engineering really depends on the data, I mean by this, like video game sales vary a lot, okay? So for example, here we have, it's in float, but we have some video games that sell, for example, $10, and other video games that sell millions of dollars. This huge gap usually is bad for our model because of the magnitude difference. Our data becomes too skewness. So to reduce that, we can apply, for example, a log transformation in our target, because our target is the sales. So just apply a log transformation. It will reduce this gap. We train, we split it, and let's encode the category features. On encoder, feed on the train, and only transform on test. The same. Let's see if the rows match. It matches, so we can concat them because we separated numerical and categorical features. Again, decision trees, you don't need to scale them. So let's just train a model. Again, we can use the criterion of squared error because it's a regression model. So we can set a max depth and a minimum samples of leaf to our tree to have, for our tree to have. We train that and we can pass the prediction, the test, and evaluate. Okay, here our model is pretty poor. Okay, it basically tells us nothing. Why is that? Because predicting a game with only a publisher, platform, and year is almost impossible, right? We cannot predict a game's global sale based on only these features. That's why I told you in the beginning that these columns is too few columns to work, but I mean, it's how regression trees work. The goal here is just to show you guys some different ways to do feature engineering and the way to train a model and evaluate it effectively. Thanks for watching and see you in the next video, guys.